The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Okay, thank you very much. So I want to start out today and talk about total water control. What do we mean when we say total water control? Why are we not saying just water control? And then I'll get into specifically water control during the transit phase of delivery. So the company I work for, Verifi, makes equipment that, among other things, measures and controls the amount of water added during transit. So we have a lot of insight into how water gets added during transit, and I'll talk about that. So when we talk about total water, what we're talking about is water from all the different sources that are added to concrete, not just water that's added at the batch plant that's metered and known very precisely, but all the water that's in the truck. Water that may be residual from the prior load, water that comes in as part of the aggregate moisture, water that comes in during washdown, water that's added by the driver, and water that's added on the site by the contractor. Some of those we can measure very precisely, we can control very accurately. Others are less, we know less precisely. So I'll talk about strategies of how to manage those sources. So first about the sources, then about adding water, and then about adding admixture during transit. Then talk about automated equipment to help manage this whole process and make it more precise. And then talk about, if we're adding these materials during transit, how to make sure that they're mixed in properly and have the proper effect on the concrete. And then wrap things up with conclusions. So as I just mentioned, water is added from a number of different sources. I've broken them out here into the 5 major categories of water and identified by percent of the total water that's added, and then how accurately we typically measure. So if we start out at the beginning of the load, before the truck is loaded, there's residual water left from washing down of the prior load, and the driver should reverse the drum and back all that water out. Sometimes it happens, it doesn't always happen. And so there can be a small percentage of water, and you can't really accurately measure that amount of water in the truck. The next is the aggregate free water, which can contribute between 10 to 40%. If you have moisture probes, and those moisture probes are well calibrated, you can get a reasonable estimate of the amount of water. But as we all know, that's not always the case. And every plant in the U.S. does not have well-calibrated, well-functioning probes. So there's some additional uncertainty that's introduced just from the free water from the aggregate. The next source is the one we can measure the most accurately. It's also the biggest source of water, and it's the metered water that goes in at the batch plant. And assuming that your meter is accurate, you can measure that very accurately. Next is, so the truck is loaded, all the water goes in, and the next step is the driver goes over to wash down the truck. Sometimes it's called the slump rack because they make the adjustment to the slump here by adding water. And again, this is not always accurate measure. Sometimes there's an external hose at the wash rack where they're adding water. Sometimes they're adding it from the tank on the truck. This rarely gets measured accurately. And then the last time is after you've left the wash rack, whether you're on the way to the job site or you're at the job site, there's additional driver added water. Sometimes that's accurately recorded. It should be accurately recorded, but oftentimes it's not. So when we look at adding up all these different sources of water, there's uncertainty in knowing how much total water is added in the concrete. And even if we can measure the batch water very accurately, we don't necessarily know how much to put in because we don't know all the other sources. So when we see on a batch ticket that there were 30.63 gallons per cubic yard of water added, it doesn't necessarily mean that that we know to that level of precision that much water went into the truck. So that's basically the challenge and what we're going to try to address in this session today. So one of the things I mentioned is when the truck finishes batching, it goes to the wash rack or the slump rack. One of the first things that the trucks often do is check the slump. And this is a reasonable thing to do because water tends to be the biggest source of variation during batching. If you're looking within a given day, biggest source of variation is likely in the water content, and it has a large effect on slump. So if your slump is varying, that's probably a good place to look is the water content. It could be that the aggregate moisture has changed. It could be that the driver has left residual water in the drum. So it's very reasonable to do. And you take it a step further and adjust to a constant target slump for a given mix design. And so you think about this in a central mix plant, they will adjust to reach a constant mixer power level, so a constant amperage on the amp meter. In a dry batch plant, the driver can make the manual adjustment to that. So that is not an unreasonable way to go, certainly, given the fact that water has a significant effect on slump, and it's one of the largest sources of variation. And so you can take data and show that the variability in water is reduced by doing that, provided you're controlling other sources of variation. The challenge is, though, that once the truck leaves the plant, additional sources of variation are introduced. So really what's the key challenge is that for a ready-mix producer, he has to batch the concrete at the plant so that it's at a certain slump sometime later. And he doesn't know everything that's going to happen from batching to the site. He doesn't know how long the transit time is going to happen. He doesn't necessarily know what the weather is going to be. He doesn't know what kind of job site delays are going to occur. He doesn't know if the driver is going to mix the concrete properly. And so there's a lot of uncertainty there. And then there's limited data about what happens when the truck reaches the site. How much water was actually added? What was the actual slump at delivery? So there's a big challenge here of not knowing once you get if you batch everything perfectly at the plant, what's going to happen after you leave the plant. And so we can just think about two scenarios. If you have the same mix design and it goes to two different sites, you have one that's a 10-minute drive away, the other that's a 60-minute haul, and the weather is much different, and the slumps that are delivered are much different. The water added to that same mix design is going to vary significantly, and that's going to cause variability in other properties of the concrete. So certainly, when you're designing a mix, you're going to take into account the fact that there's going to be some variability here. There will be some water added. If you could take it a step further and actually measure and control what's going on, you can help reduce some of that variation. The other challenge of making the adjustments is that the slump, we're making adjustments to slump on the job site, but we don't necessarily know the slump well, so it's often not measured on every load, and often adjustments are made to the water content at the site based on a visual estimate of slump. And then contractors often order one slump, and then they said they want a different slump on the job site, so they raise a slump. And so there's disputes over what is actually a 3-inch slump. Is a 3-inch slump what you see on the left? Is it what you see on the right? So the contractor may say, I want a 3-inch slump, and in his mind, that's what you see on the right. So there's additional variability just in the slump. So if you're adjusting to slump with water at the job site and you're not measuring the slump accurately, then obviously you're going to get more variability in the total water content added. How can we address that? Well, one way is, obviously as I alluded to before, is measuring the slump and measuring the amount of water added and controlling the amount of water added. The other way is to use admixture to achieve the target slump. So if you think about this, when we're at the plant, we can make adjustments, we can control to a consistent slump, or use slump to help us identify variability in water content. When the truck leaves the site, we get more, when the truck leaves the plant and goes to the site, we get more sources of variability introduced. And so to accommodate those, if we adjust with Superplasticizer and water, we'll have less water used and less variation in water. So just to summarize some of the recommendations on how to manage total water content, and particularly what happens in the delivery phase. First of all, manage all the sources of water. So we listed them all. Make sure that the driver reverses or backs out the drum to remove all the residual water. Next, make sure that the aggregate is measured accurately, and there will be another presentation about that this morning. Limit the amount of washed-down water and accurately measure what water is added on the truck so you know how much goes in. Also accurately measure the slump. Don't rely on visual assessments. Control the right slump. So don't allow unauthorized changes. Don't allow the contractor to make a change to the slump. And then once you're measuring the amount of water, make sure that amount of water does not exceed the designed water to cementitious materials ratio. And then, if where possible, adjust with admixture once you've reached that maximum water cement ratio. So there are tools now available that will help automate that process, automate those recommendations, and that will help reduce the amount and the variation in the water added to the truck. I will refer to data this morning from the Verifi concrete control system, which you see here. And what this system does is it measures the slump and the temperature of the concrete in the mixer. It also measures the drum speed and the amount of water added. Based on those slump measurements, it can add water or superplasticizer to reach a slump target, and that can be done automatically. So you set the target slump, and the system automatically determines and adds the correct dose to reach the slump, or manually. The driver can go in and manually put in however much admixture is necessary. It then prompts the driver to ensure that the concrete is fully mixed. So one of the things is when you're putting water in admixture, as we'll talk about later, it's very important to make sure that gets fully mixed. And so you need a way to validate that. And then you get documentation of the delivery process, how much water was added, how much admixture was added, and what the final slump and temperature were. And then based on that data, you can go in and make changes to your ready-mix operation. So here's a layout of the system on a truck. So the slump is based on hydraulic pressure and drum speed, as well as the load size. So those are measured on the truck. The first two, the hydraulic pressure and drum speed. There's also a temperature sensor mounted on the hatch of the drum. There's an existing water nozzle, and then added to that is an admixture nozzle to inject the chemical so that it gets injected under high pressure and reaches the concrete. There's an external slump display. There's an admixture tank, obviously, flow valves and flow meters to measure and add water and admixture. There's a control box near the center of the truck that's the brains of the operation, and then there's an in-cab interface for the driver. Everything on the truck communicates wirelessly with a gateway in the plant, just a black box that sits in the plant, has a radio, and then it connects via the internet to the back end database where all the data is stored. And then from that data, reports are generated and feedback is given to the batch operator. Let me show you some data. So first of all, is the slump measurement accurate? So here's data comparing the ASTM slump measured with the cone to the slump measured with the automated system, and you can see high correlation between the two slumps, an R-squared of 0.95. And this data that's shown here was actually from 3 different trucks at 2 plants. So this wasn't just one truck. These are different trucks, different plants, different materials. So now let's talk about adding admixture on the truck. And so how does this work? This is people have been adding admixture for several decades on the job site, but not necessarily the way that you can do it with some of these new types of equipment. So how does this work? So the first thing is that the ready-mix producer will go in and set through a web application how the admixture is to be added. So you can see part of that screen here where you can decide whether you want the admixture to be added automatically, manually, some of both. You can set the maximum admixture amount, and some other parameters. And the key thing here again is that we're not putting in a fixed dose of admixture. We're setting the slump and then letting the system determine the correct dose to get to that slump, subject, of course, to the maximum admixture used. So the admixture is loaded into the tank, and then it's injected under pressure in a very small stream of material that goes in, so that that highly potent admixture does not get on the fins of the truck, but actually gets onto the concrete. So here's a typical delivery cycle with adding both water and admixture. So you can see the slump over time. Slump is shown here, and then at the bottom, water and admixture. So you can see initially our slump was below target, so we added water automatically to bring it to the target. Once we had the batch target reached, we then increased to the delivery target by adding admixture, and we maintained admixture. So we reached the target slump here, but as the transit time was extended and slump loss occurred, further admixture was automatically added, as you see down here. So again, if you look at managing water with admixture addition, if you look through 4 scenarios here of adding water, and what is going to be our amount and variation in water. So I've got a couple graphs here to illustrate this conceptually. So if you think about it, you're going to have a maximum water content that's from your design. So you have a certain amount of water that you cannot exceed. The reasonable thing to do, of course, is to batch below that, so that you have additional water to take into account variations that are going to occur, to take into account the fact that you'll have slump loss during delivery. And so if you're batching without having an automatic slump control at the plant, you're going to have a certain variability in batching. Because we mentioned that before, you have all these different sources of water. There's variations in some of those sources. You're going to have a certain level of variation, and you can certainly manage this a number of ways and keep this low, but there will inevitably be some variation. If you're adjusting to slump with water right after batching, you can reduce some of that variation. You're not going to eliminate it, obviously, because there's other sources of variation that are occurring, but it is one way to reduce variation. Then when you go to water at delivery on the right, you can see we've left the plant, we've gone to the job site, it's sometime later in the future. The amount of water that you add is obviously going to go up if you're adding water. And because you have differences in weather, differences in transit time, there's going to be some additional variation introduced above and beyond what was there at batching, very likely. But if you're just dealing with admixture, obviously you're not adding into that variation. And so the amount of water and the variation in water is less. So that's conceptually how, by adding admixture instead of water in transit, you can reduce variation, increase strength, improve other properties, and have an opportunity to reduce some of the cementitious materials content. The other thing is, I mentioned before that the slump at discharge is often controversial at the job site because the contractor wants one thing. He wants his slump, and he wants it at whatever water content is necessary to get to that slump, as long as you don't exceed the water to cement ratio. So very often what happens is the concrete is ordered at one slump, but from the data that we have, and this is sample data from Verifi systems, the actual slump at delivery is higher because the contractor wants a higher slump, and there's a lot of variation. So what you see here is this is with just measuring the slump, and actually not even showing it to people, not even showing it to the driver or the contractor, just measuring it in the background. What is the difference in slump versus the target? So if you're at 0, that means you're right on target. And you can see that on average, the slump was about 2.8 inches above target at delivery, and the standard deviation in slump was also quite high, 2.5 inches. When you had automatic slump control, this is at the job site, so we're still adding water as we go to the job site. We're getting more consistent final slump. Just the fact that you have more consistent final slump is going to reduce the variation in total water, obviously, because they're adding water to exceed this slump. And so this is not even putting in an admixture yet. So you get further benefit when you put in water, when you put in admixture. And also the fact that you're just measuring and displaying what the slump is, it helps reduce some of those controversies at the job site. So like I said before, The ready-mix producer has what he considers a 3-inch slump. The contractor has what he considers a 3-inch slump, and they're not necessarily what the cone measurement says is a 3-inch slump. And so I mentioned, and just to build on that, the data that's generated and how that can help manage the process and reduce the variation in water. When you've got the whole team that's producing the concrete and they've all got data and they're all working together, you can reduce some of the variation. So when you have data, for example, with the Verifi system, you have, for example, the batch operator has data on the slumps as they were batched and how much water the driver had to add to reach the batch slump. That can help him batch more accurately. The drivers have an in-cab interface that shows them what the actual slump is, shows them how much water, how much admixture is needed to reach the target slump. And they don't have to make a visual assessment or guess what the slump is. They know exactly what it is. And then there's reports after the fact that go in and summarize a week's worth of data or a month's worth of data and show the reduction or show where the variation is and let QC and operations personnel help reduce that variation. Another question is, can admixture be fully mixed in transit? It's a good question, and I'll show some brief data here. Here's an admixture that's being added, and you can see we're measuring the slump from Verifi over time, and you can see that we mixed at two different speeds. We mixed at 12.5 RPM and at 2.6 RPM. And obviously mixing at 2.6 RPM took more time, but if you look at the number of revolutions, the number of revolutions was about the same. So when you're mixing, you need to get a certain number of revolutions and to make sure that you get the concrete fully mixed. And you can get it mixed even at low speed, at 2.6 RPM. And then here's a graph showing different admixtures. So you can see that two different polycarboxylate admixtures, one required about 30 revolutions, the other 60 to be fully mixed. So again, it's revolutions, it's the admixture, it's the mix design that really determine how much mixing is required. So you can look for your admixture, your materials, you're going to need a certain number of revolutions. So what are the benefits of adding admixture at the job site? First of all, you can compensate for variations in haul time, weather, other factors without having to add water, without having to increase the amount or the variation and the total water that's added. You get consistent final slump, and consistent final slump means consistent other properties. It means that your air content's more consistent, your strength is more consistent, and so forth. There's, as I mentioned, less amount of variation in water. Also, you're able to transport larger loads. So you can start out with a low slump and then bring it to a high slump on the job site. It could have, if you're in a very hilly area and you have a full-size load, you can't often transport very high slumps because of the risk of spillage. So with adding admixture at the job site, you can start out with a lower slump and then go to a high slump. And then obviously for long hauls, you don't have to maintain this high slump for the entire transit time. You can wait and you can conserve admixture by adjusting at the job site. And by doing it in an automated fashion rather than a manual fashion where the driver's got to get out and manually pour in admixture, or you have to have manual tanks and dispensers on the job site, automated addition can ensure that the correct dose is added, that the concrete gets fully mixed prior to discharge, that the slump is correct, and then obviously you don't have to deal with manual additions. To wrap things up, we said that water is added from a number of different sources, and so you've got to have a strategy to manage all these different sources, and it's a big task, and it's a big challenge. But there's technology now available to help reduce those variations by measuring the slump accurately, so you know exactly what you're delivering, by automating water addition, by measuring the amount of water that goes in, so you know exactly how much goes in, and you're not exceeding your water to cementitious materials ratio. And you can add admixture, so you're adding admixture instead of water, and that reduces the amount of variation of water. And we can add Superplasticizer in transit and make sure it's fully mixed. You've got to make sure it's fully mixed. That's very important. But you can get documentation of the fact that it is fully mixed. With these strategies, you can help reduce and manage the amount of total water that's added to the concrete mix. Thank you very much.
Okay. That was great. It was a great presentation, Eric.
Okay.
And one thing I'd like to indicate is that on every job, a method of job site slump adjustment should be agreed on by the owner's rep and the contractor and the ready-mix supplier. Okay, there should be a method, and you've indicated why this is desirable. The other thing, depending on the application, I don't want to have varying amounts of admixture incorporated in the load. For example, if I'm finishing a concrete slab, I want to have a uniform quantity of admixture because of the set time variation induced by admixtures. So if we can modify your proposal to account for the application of the concrete, that'd be fabulous. And the other thing you brought up is something that ready-mix people don't necessarily do automatically, and that is drums should be reversed when they pull under the truck pulls under the tipple. Mm-hmm. If you're serious about control of concrete quality, you've got to start off with an empty drum.
Mm-hmm. Yes.
Thanks for the enlightenment.
Okay, thank you very much. And yes, you make a good point about the admixture and not wanting variations in admixture. So I think a lot of it depends on the admixture selection. Becomes very critical that you want to pick the right admixture for the application. That if there's some admixtures that as you vary the dose, you're going to get more variation in things like setting time. Some admixtures you're going to have less variation in setting time. So, and then obviously you can set a fixed dose if that's what you desire.
On the issue of the correlation between slump and water content, and I understand how you can do that as long as all other factors remain constant. But given that typical slump loss rates, depending on temperature, can be easily 2 to 3 inches per hour, therefore there has to be a time component in the correlation. And also given that we like to talk about other factors being constant, but air content never is, how do we deal with the water content slump correlation given time variations and the unavoidable high variability in air content?
Mm-hmm. Right. Well, I think on the first question with the time factor and the slump loss over time is what we're recommending is that if you're going to do that adjustment, do it at the plant, not at the site, because you're going to have differences in time, differences in slump loss. So unless you want to go out and model that and have ways to account for that, it's really best to do the water adjustment at the site. Or at the plant.
So the water slump correlation is established at the plant.
Right.
Okay.
Mm-hmm. Yes.
And about air?
The air is another thing that's got to be managed as well. That's another thing that certainly if your air is varying, that correlation is going to be off. But that said, if you look at the total reduction in variability, you're still going to have in most cases we've seen that that even if there's some variability in the air, that there's an overall less variation by adjusting to slump with water at the plant. And then also having more consistent water leads to more consistent air content.
I guess another possibility there would be when you do your water content slump correlation, always make sure you take an air test, and then you just have a slump or water content slump air correlation, and maybe knock it out. Thank you.
Exactly. Thanks.